Hi everyone, welcome to Tutorial 2. Now that we've spent some time learning about the types of paleoclimate archives that exist, we'll go into further detail about the specific archives and proxies that are used to reconstruct changes in the ocean, atmosphere, and terrestrial climate systems. To start out, we'll investigate marine paleoclimate archives and proxies. There are many climate variables that we can reconstruct from marine climate proxies. And some common marine climate variables that we can reconstruct using paleoclimate proxies include ocean salinity, primary productivity, and sea surface temperature. Today, and in this tutorial, we'll mostly focus on sea surface temperature reconstructions based on marine paleoclimate records. Two archives for reconstructing sea surface temperature are marine sediment cores and corals. In marine sediments, common proxies include organic biomarkers and oxygen isotopes. In corals, the common proxies are layer growth and oxygen isotopes. And you'll notice that a common proxy in both of these archives are these oxygen isotopes that I've mentioned. And they're measured on different materials in both of these archives. In marine sediments, oxygen isotopes are measured on foraminifera, or forams. Forams are single-celled marine organisms that have calcium carbonate shells, and the shells of these organisms get preserved in the sediment, and oxygen isotopes of these shells can be measured. In corals, the coral itself is made of calcium carbonate, and that's where we can measure the oxygen isotopes. But what exactly are oxygen isotopes, and how do they record changes in sea surface temperature? Isotopes are elements with the same number of protons and electrons, but a different number of neutrons. The two most common oxygen isotopes are oxygen 16, which is the lighter isotope, and oxygen 18, which is the heavier isotope. And the ratio of the heavy oxygen relative to the light oxygen can be measured in materials containing oxygen, such as seawater. And this ratio is referred to as delta 18O, and the units for this are per mil. So how does this relate to sea surface temperature? The ratio of oxygen isotopes in seawater varies in response to ocean temperature. Specifically, when sea surface temperature is cooler, there's less of the light isotope in the water, and this results in a more enriched delta 18O. When there's a warmer sea surface temperature, there's more of the light isotope in the water, so this results in a depleted delta 18O. And we'll go into some more details about isotopes and how they record changes in climate in tutorials later today. So now that we have an idea of how oxygen isotopes record changes in sea surface temperature, we're still missing the link between the oxygen isotopes of the seawater and the oxygen isotopes of the forams, or the corals. For today, for this tutorial, we'll focus on corals. And in later tutorials today, we'll spend some more time thinking about oxygen isotopes of forams. So for now, thinking about corals, since corals are made of calcium carbonate, they incorporate the seawater oxygen isotopic signature into their structure. Therefore, by measuring the oxygen isotopes of the corals in each layer, this can record changes in seawater oxygen isotopes, and can therefore record changes in sea surface temperature over time. Coral-based sea surface temperature reconstructions tend to be very high resolution, and this makes them especially useful for understanding short-term climate phenomena. For example, one climate phenomenon that coral-based sea surface temperature reconstructions are commonly used to interpret is the El Niño Southern Oscillation. El Niño Southern Oscillation, or ENSO, is a climate phenomenon that originates in the tropical Pacific Ocean, but has global impacts on atmospheric circulation, temperature, and precipitation. We've already spent some time learning about ENSO in day 1 and day 2 of this course, but as a brief reminder, there are two main phases of ENSO, El Niño and La Niña. El Niño is characterized by warmer than average sea surface temperatures in the central and eastern tropical Pacific, and La Niña is characterized by cooler than average sea surface temperatures in the central and eastern tropical Pacific. In this tutorial, we'll explore records of sea surface temperature over the past 120 years based on reconstructions of oxygen isotopes from coral, and we'll use these to understand past changes in the ENSO in the tropical Pacific Ocean.